your base Rust knowledge by applying Rust to examples from the field of systems programming. Every chapter includes at least one large project that includes a new language feature. You will build command line utilities, libraries, graphical applications, networked applications, and even your own operating system kernel. Chapter 5. Data in Depth. This chapter covers learning how the computer represents data, building a working CPU emulator, creating your own numeric data type, understanding floating point numbers. This chapter is all about understanding how zeros and ones can become much larger objects like text, images, and sound. We'll also touch on how computers do computation. By the end of the chapter, you will have emulated a fully functional computer with CPU, memory, and user-defined functions. You will break apart floating point numbers to create a numeric data type of your own that only takes a single byte. The chapter introduces a number of terms, such as endianness and integer overflow, that may not be familiar to programmers who have never done systems programming. Section 5.1. Bit patterns and types. A small but important lesson is that a single bit pattern can mean different things. The type system of a higher level language, such as Rust, is just an artificial abstraction over reality. Understanding this becomes important as you begin to unravel some of that abstraction to gain a deeper understanding of how computers work. Listing 5.1 in this file is an example that uses the same bit pattern to represent two different numbers. The type system, not the CPU, is what makes this distinction. The following shows the listing's output. The different mapping between bit strings and numbers explains part of the distinction between binary files and text files. Text files are just binary files that happen to follow a consistent mapping between bit strings and characters. This mapping is called an encoding. Arbitrary files don't describe their meaning to the outside world, which makes these opaque. We can take this process one step further. What happens if we ask Rust to treat a bit pattern produced by one type as another? The following listing provides an answer. The source code for this listing is in this file. When compiled and run, the code from listing 5.2 produces the following output. Some further remarks about some of the unfamiliar Rust that listing 5.2 introduces includes the following. Line 8 demonstrates a new directive to the println exclamation point macro, :032b within curly braces. The 032 reads as left pad with 32 zeros, and the right-hand B invokes the std fmt binary trait. This contrasts with the default syntax of open-close curly braces, which invokes std fmt display trait, or the question mark syntax, :question mark within curly braces, which invokes the std fmt debug. Unfortunately for us, F32 doesn't implement the std fmt binary. Luckily, Rust's integer types do. There are two integer types guaranteed to take up the same number of bits as F32, I32 and U32. The decision about which to choose is somewhat arbitrary. Lines 3 through 5 perform the conversion discussed in the previous bulleted point. The std-mem transmute function asks Rust to naively interpret an F32 as an U32 without affecting any of the underlying bits. The inverse conversion is repeated later on lines 10 through 12. Mixing data types in a program is inherently chaotic, so we need to wrap these operations within unsafe blocks. Unsafe tells the Rust compiler, "Stand back, I'll take care of things from here. I've got this." It's a signal to the compiler that you have more context than it does to verify the correctness of the program. Using the unsafe keyword does not imply that the code is inherently dangerous. For example, it does not allow you to bypass Rust's borrow checker. It indicates that the compiler is not able to guarantee that the program's memory is safe by itself. Using unsafe means that the programmer is fully responsible for maintaining the program's integrity. Warning: some functionality allowed within unsafe blocks is more difficult to verify than others. For example, the std-mem transmute function is one of the least safe in the language. It shreds all type safety. Investigate alternatives before using it in your own code. Needlessly using unsafe blocks is heavily frowned upon within the Rust community. It can expose your software to critical security vulnerabilities. Its primary purpose is to allow Rust to interact with external code, such as libraries written in other languages and OS interfaces. This book uses unsafe more frequently than many projects because its code examples are teaching tools, not industrial software. Unsafe allows you to peek at and poke at individual bytes, which is essential knowledge for people seeking to understand how computers work. Section 5.2. Life of an integer. During earlier chapters, we spent some time discussing what it means for an integer to be an I32, an U8, or an U size. Integers are like small, delicate fish. They do what they do remarkably well, but take them outside of their natural range and they die a quick, painful death. Integers live within a fixed range. When represented inside the computer, these occupy a fixed number of bits per type. Unlike floating point numbers, integers cannot sacrifice their precision to extend their bounds. Once those bits have been filled with ones, the only way forward is back to all zeros. A 16-bit integer can represent numbers between 0 and 65,535 inclusive. What happens when you want to count to 65,536? Let's find out. The technical term for the class of problem we are investigating is integer overflow. One of the most innocuous ways of overflowing an integer is by incrementing forever. The following listing, ch5/ch5-2-oblivion.rs, is a trivial example of this. When we try to run listing 5.3, things don't end well for our program. Let's look at the output. A panicked program is a dead program. Panic means that the programmer has asked the program to do something that's impossible. It doesn't know what to do to proceed and thus shuts itself down. To understand why this is such a critical class of bugs, let's look at what's going on under the hood. Listing 5.4, ch5/ch5-bit-patterns.rs, prints 6 numbers with their bit patterns laid out in literal form. When compiled, the listing prints the following short line. Try compiling the code with optimizations enabled via rustc-o ch5-2-oblivion.rs and running the resulting executable. The behavior is quite different. The problem we're interested in is what happens when there's no more bits left. 65,536 cannot be represented by U16. There's another easy way to kill a program using a similar technique. In listing 5.5, we ask Rust to fit 400 into a U8, which can only count up to 255 values. Look in this file for the source code for this listing. The code compiles, but one of two things happen. The program panics. This behavior can be invoked via executing rustc with its default options. The program gives you the wrong answer. This behavior can be invoked by executing rustc with the -o flag. rustc-o ch-impossible-add.rs &ch-impossible-add. There are two small lessons here. It's important to understand the limitations of your types. Despite Rust's strengths, programs written in Rust can still break. Developing strategies for preventing integer overflow is one of the ways that systems programmers are distinguished from others. Programmers who have only experience with dynamic languages are extremely unlikely to encounter integer overflow. Dynamic languages typically check to see that the results of integer expressions will fit. When these can't, the variable that's receiving the result is promoted to a wider integer type. When developing performance-critical code, you get to choose what parameters to adjust. If you use fixed size types, you gain speed, but you need to accept some risk. To mitigate the risk, you can check to see that overflow won't occur at runtime. Imposing those checks will slow you down, however. Another much more common option is to sacrifice space by using a large integer type such as I64. To go higher still, you'll need to move to arbitrarily sized integers, which come with their own costs. Section 5.2.1 Understanding Endianness. CPU vendors argue about how the individual bytes that make up integers should be laid out. Some CPUs order multi-byte sequences left to right, and others are right to left. This characteristic is known as a CPU's endianness. This is one of the reasons why copying an executable file from one computer to another might not work. Let's consider a 32-bit integer that represents a number made up of 4 bytes, AA, BB, CC, and DD. Listing 5.6 in this file, with the help of our friend sysmemtransmute, demonstrates that byte order matters. When compiled and executed, the code from listing 5.6 prints one of two things, depending on the endianness of your machine. Most computers that people run for day-to-day work print the following. Footnote 1. In 2021, the x86-64 AMD 64 CPU architecture is dominant. But more exotic hardware swaps the two numbers around like this. The terminology comes from the significance of bytes in the sequence. To take you back to when you learned addition, we can factor the number 123 into 3 parts. Summing all these parts gets us back to our original number. The first part, 100, is labeled as the most significant. When written out in the conventional way, 123 as 123, we are writing in big endian format. Were we to invert that ordering by writing 123 as 321, we would be writing in little endian format. Binary numbers work in a similar way. Each number part is a power of 2, 2 to the 0, 2 to the first, 2 to the second, 2 to the end, rather than a power of 10, 10 to the 0, 10 to the first, 10 to the second, 10 to the end. Before the late 1990s, endianness was a big issue, especially in the server market. Glossing over the fact that a number of processors can support bidirectional endianness, Sun Microsystems, Cray, Motorola, and SGI went one way. ARM decided to hedge its bets and develop a bi-endian architecture. Intel went the other way. The other way won. Integers are almost certainly stored in little endian format. In addition to multi-byte sequences, there is a related problem within a byte. Should a U8 represent 3 look like 000_0011, or should it look like 1100_000? The computer's preference for layout of individual bits is known as bit numbering or bit endianness. It's unlikely, however, that this internal ordering will affect your day-to-day programming. To investigate this further, look for your platform's documentation to find out which end its most significant bit lies. Note: the abbreviation MSB can be deceptive. Different authors use the same abbreviation to refer to two concepts, most significant bit and most significant byte. To avoid confusion, this text uses the term bit numbering to refer to the most significant bit and endianness to refer to the most significant byte. Section 5.3. Representing decimal numbers. One of the claims made at the start of this chapter was that understanding more about bit patterns enables you to compress your data. Let's put that into practice. In this section, you will learn how to pull bits out of a floating point number and inject those into a single byte format of your own creation. Here is some context for the problem at hand. Machine learning practitioners often need to store and distribute large models. A model for our purposes here is just a large array of numbers. The numbers within those models often fall within the ranges 0 equals 1 or -1 equals 1, using Russ range syntax, depending on the application. Given that we don't need the whole range that F32 or F64 supports, why use all of these bytes? Let's see how far we can get with one. Because there is a known limited range, it's possible to create a decimal number format that can model that range compactly. To start, we're going to need to learn about how decimal numbers are represented inside today's computers. This means learning about the internals of floating point numbers. Section 5.4, Floating Point Numbers. Each floating point number is laid out in memory as scientific notation. If you're unfamiliar with scientific notation, here is a quick primer. Scientists describe the mass of Jupiter as 1.898 times 10 to the 27th kilograms, and the mass of an ant as 3.801 times 10 to the -4th kilograms. The key insight is that the same number of characters are used to describe vastly different scales. Computer scientists have taken advantage of that insight to create a fixed-width format that encodes a wide range of numbers. Each position within a number in scientific notation is given a role. A sign, which is implied in our two examples, would be present for negative numbers, negative infinity to 0. The mantissa, also known as the significand, can be thought of as being the value in question. 1.898 and 3.801, for example. The radix, also known as the base, is the value that is raised to the power of the exponent, 10 in both of our examples. The exponent describes the scale of the values, 27 and -4. This crosses over to floating point quite neatly. A floating point value is a container with 3 fields: a sign bit, an exponent, a mantissa. Where is the radix? The standard defines it as 2 for all floating point types. This definition allows the radix to be omitted from the bit pattern itself. Section 5.4.1, Looking inside an F32. Figure 5.1 represents the memory layout of the F32 type in Rust. The layout is called binary 32 within the IEEE 754-2019 and IEEE 754-2008 standards, and single by their predecessor IEEE 754-1985. The value 42.42 is encoded as F32 with the bit pattern shown here. That bit pattern is more compactly represented as 0 times 4229AE14. Table 5.1 shows the values of each of the 3 fields and what those represent. Note: see lines 32 through 38 of listing 5.10 and the explanation provided shortly in section 5.3.5 to learn how this binary number represents 1.325625. The following equation decodes the fields of a floating point number into a single number. Variables from the standard, radix, bias, appear in title case. Variables from the bit pattern, sign_bit, mantissa, exponent, occur as lowercase and monospace. One quirk of floating point numbers is that their sign bits allow for both 0 and -0. That is, floating point numbers that have different bit patterns compare as equal, 0 and -0, and have identical bit patterns, NaN values, that compare as unequal. Section 5.4.2, Isolating the sign bit. To isolate the sign bit, shift the other bits out of the way. For F32, this involves a right shift of 31 places, or greater than 31. The following listing is a short snippet of code that performs the right shift. To provide you with a deeper intuition about what is happening, these steps are detailed graphically here. 1. Start with an F32 value. 2. Interpret the bits of the F32 as a U32 to allow for bit manipulation. 3. Shift the bits within N 31 places to the right. Section 5.4.3. Isolating the exponent. To isolate the exponent, 2 bit manipulations are required. First, perform a right shift to overwrite the mantis's bit, greater than 23. And then use an AND mask, ampersand 0 times FF, to exclude the sign bit. The exponent's bits also need to go through a decoding step. To decode the exponent, interpret its 8 bits as a signed integer, then subtract 127 from the result. As discussed in section 5.3.2, 127 is known as the bias. The following listing shows the code that describes the steps given in the last 2 paragraphs. And to further explain the process, these steps are repeated graphically as follows. 1. Start with an F32 number. 2. Interpret the bits of that F32 as U32 to allow for bit manipulation. 3. Shift the exponent's 8 bits to the right, overwriting the mantissa. 4. Filter the sign bit away with an AND mask. Only the 8 rightmost bits can pass through the mask. 5. Interpret the remaining bits as a signed integer and subtract the bias as defined by the standard. Section 5.4.4. Isolate the mantissa. To isolate the mantissa's 23 bits, you can use an AND mask to remove the sign bit and the exponent, ampersand 0 times 7FFFFF. However, it's actually not necessary to do so because the following decoding steps can simply ignore bits as irrelevant. Unfortunately, the mantissa's decoding step is significantly more complex than the exponents. To decode the mantissa's bits, multiply each bit by its weight and sum the result. The first bit's weight is 0.5, and each subsequent bit's weight is half of the current weight. For example, 0.5, 2 to the minus 1, 0.25, 2 to the minus 2, and so on, until this number times 2 to the minus 23rd. An implicit 24th bit that represents 1.0 times 2 to the minus 0 is also considered to be on, except when special cases are triggered. Special cases are triggered by the state of the exponent. When the exponent's bits are all zeros, then the treatment of the mantissa's bits change to represent subnormal numbers, also known as denormal numbers. In practical terms, this change increases the number of decimal numbers near 0 that can be represented. Formally, a subnormal number is one between 0 and the smallest number that normal behavior would otherwise be able to represent. When the exponent's bits are all ones, then the decimal number is infinity, negative infinity, or not a number, or nan. Nan values indicate special cases where the numeric result is mathematically undefined, such as 0 divided by 0, or that are otherwise invalid. Operations involving nan values are often counterintuitive. For example, testing whether 2 values are equal is always false, even when the 2 bit patterns are exactly the same. An interesting curiosity is that F32 has approximately 4.2 million, or 2 to the 22nd, bit patterns that represent nan. The following listing provides the code that implements non-special cases. Repeating that process slowly. 1. Start with an F32 value. 2. Cast F32 as U32 to allow for bit manipulation. 3. Create a mutable F32 value initialized to 1.0, or 2 to the minus 0. This represents the weight of the implicit 24th bit. 4. Iterate through the fractional bits of the mantissa, adding those bits to find values to the mantissa variable. A. Iterate from 0 to 23 with the temporary variable I assigned to the iteration number. B. Create a bit mask with the iteration number as the bit allowed to pass through and assign the result to mask. For example, when I equals 5, the bit mask is this. C. Use mask as a filter against the bits from the original number stored as n_bits. When the original number's bit at position I is non-zero, 1_at_bit_I will be assigned to a non-zero value. D. If 1_at_bit_I is non-zero, then proceed. E. Calculate the weight of the bit at position I, which is 2I to the minus 23rd. F. Add the weight to mantissa in place. Parsing Rust's floating point literals is harder than it looks. Rust numbers have methods. To return the nearest integer to 1.2, Rust uses the method 1.2_f32.ceil, rather than the function call ceil of 1.2. While often convenient, this can cause some issues when the compiler parses your source code. For example, unary minus has lower precedence than method calls, which means unexpected mathematical errors can occur. It is often helpful to use parentheses to make your intent clear to the compiler. To calculate -1 to the 0, wrap 1.0 in parentheses, rather than, which is interpreted as minus open paren 1 to the 0 close paren. Because both -1 to the 0 and minus open paren 1 to the 0 close paren are mathematically valid, Rust will not complain when parentheses are omitted. Section 5.4.5. Dissecting a floating point number. As mentioned at the start of Section 5.4, floating point numbers are a container format with 3 fields. Section 5.4.1 through 5.4.3 have given us the tools we need to extract each of these fields. Let's put those to work. Listing 5.10 does a round trip. It extracts the fields from the number 42.42 encoded as an F32 into individual parts, then assembles these again to create another number. To convert the bits within a floating point number to a number, there are 3 tasks. 1. Extract the bits of those values from the container, 2_parts, on lines 1 through 26. 2. Decode each value from its raw bit pattern to its actual value. Decode on lines 28 through 47. 3. Perform the arithmetic to convert from scientific notation to an ordinary number, from _parts, on lines 49 through 55. When we run listing 5.10, it provides 2 views of the internals of the number 42.42 encoded as an F32. In listing 5.10, deconstruct _F32 extracts each field of a floating point value with its bit manipulation techniques. Decode _F32_parts demonstrates how to convert those fields to the relevant number. The F32_from_parts method combines these to create a single decimal number. The source for this file is located in this file. Understanding how to unpack bits from bytes means you'll be in a much stronger position when you're faced with interpreting untyped bytes flying in from the network throughout your career. Section